Okay, so people are studying. Ready? People are studying world happiness. Apparently, there was a survey, and participants rated happiness on a scale of 0 to 10. 0 means worst possible life, 10 means best possible life. They give you in the problem that X is normally distributed with mean 5.4 and a standard deviation of 2.2. So the average happiness score is 5.4, which is that. So we want to find the probability of X less than 4. If you can't do this mentally, what are you supposed to do? Draw it out.
How would you do it?
What?
How would you do it mentally?
I don't know your brain, so my that's different from yours.
Okay.
That's why I'm saying yes.
Okay.
So 4 is right over there. So even before you start the problem, do you believe the answer could be over 50%? No, it has to be under. Could it be close to 0?
No.
No. Could it be about 20%? Maybe, right? We don't know. So as I went around, some of you started or kept the lower limit at 0. In this problem, nothing wrong with that, but your safest bet should always be negative E99 for the lower limit. And if you're computing the area on that side, the upper limit, positive E99. That approach will work for for every problem. Good. Otherwise, you've got to tweak the upper and lower limits, and I don't want you guys to make mistakes. So, normal CDF.
So in the test, the answers will always be based on the upper and lower limits being infinity and negative infinity.
Yes. Negative E99 4. What is the mean?
5.4.
Standard deviation.
2.2.
And what do we get?
Yeah.
0.2623.
Yeah. 0.2623. So there is a 26.23% chance that a participant rated a value less than 4. If it is between 4 and 6, what is the lower limit? 4. 4. The upper limit? 6. Mean?
5.4.
Standard deviation? 2.2. What do we get?
0.3452.
3452.
3, 4, 5, 6.
2452.
3452.
Yes.
0.3452.
What's
so hard?
Okay. And lastly, greater than 8, which would mean perhaps somewhere here. Sure, the upper limit is 10, but don't put 10, put E99. It'll always work. Could the answer be 54%?
No.
Could it be 30%?
No.
Could it be 10%?
Yes.
Maybe.
Maybe.
So normal CDF. Where should we start?
8.
Where should we end?
E99.
5.4 and 2.2. What is that value? 0.1186. Now, you look at those values and we want to know if any of them are unusual. Do you believe that part A probability is unusual?
No.
No. How about part B?
No.
How about part C?
No.
So for us to say that something is unusual, we have to have a probability of less than 0.0001. Good. Remember, 3 standard deviations and 2 standard deviations. Yes.
On Pearson, it said that unusual score was less than or greater than. So Yeah, let's turn
0.025.
0.005.
0.005.
So if it is within
Yeah, I think it's
2 standard deviations, then it's okay. Anything past 2 standard deviations, then it is unusual. So 0.025 or below would be unusual. 0.0015 or below, very unusual. Good. So none of them here meet the criteria. So none of those values are unusual.
0.05.
So usual, okay values, even 3 standard deviations, it's okay. So if it goes past this value, or if it goes below x bar minus 2s, then it would be unusual. Right.
Okay.
And below, excuse me, above x bar plus 3s, below x bar minus 3s, very unusual. And this is how your book defines it. So what would the probabilities be corresponding to that? So if the probability happens to be less than 0.025, it is unusual. That's just how your book defines it. Very unusual probability less than 0.0015. Yes.
Shouldn't the one for the right be like 0.975?
The area below x bar plus 2s is 0.975. What I'm trying to say is, when do we call something unusual? If it falls over here, or if the observation falls over there. And that would happen with probability 2.5%. Yes,
Could you also think of it as how -2
you could do it that way also.
Yeah.
So sure, you can look with the -2 standard deviations and +2 standard deviations and determine whether it's from the mean and determine whether it's unusual or not, very unusual or not, but it's just extra work, right? If you find the probability and if you know this criteria, just by looking at the probability, you can conclude if something is unusual or very unusual. So in practice, there, one would consider something to be very unusual if it goes below 0.0001. But this is how your book defines it. Okay, so again, if you can't do it mentally, you're supposed to draw it out. So the mean is 100, the standard deviation is 12. So x is less than 70. You could also do this from the empirical rule. So one standard deviation, 112, 123, 136. Yes?
Yes.
Subtract on this side, have 88, 76, 64. Correct? So just by looking at it, we can sort of answer x less than 70. In other words, it's probably right over here, correct?
Yes.
Do we expect the answer to be large or small?
Very
Small. So normal CDF. Where should we start?
Negative.
End at 70, mean is 100, standard deviation is 12, and what do we get?
0.0062.
0.0062. Would we consider that unusual?
Yes.
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 More than 2 spin.
Here is unusual is a good thing, right? We'd like to have a very low utility bill, so being unusual is amazing. Between 90 and 120, so right there, perhaps about 40%, 50%, maybe, if I have to guess. Could it be?
Yeah.
It could be, but I don't know exactly. So start at 190, end at 120. The mean is 100. The standard deviation is 12, and what do we get?
0.7499.
0.7499. So 75% of the utility bills in that city is likely to fall between $90 and $120. Does that make sense? So what if your bill is bigger than 140? Definitely something unusual going on, because 140 is right over there. And we want to know what are the chances that it will exceed 140. Do we expect a very large probability or an extremely small probability? Extremely small. And if you put it in the calculator, what do we get?
0.000.
Before that step, directly you get 4.29 times
-4.
in the very corner of the spring, you will see E -4. The most common mistake is ignoring this and searching for an answer of 4.29. First off, you shouldn't be searching for 4.29, period. Why? Because it's a probability cannot exceed 1, so definitely you're doing something wrong. So this is just scientific notation. E -4 is the same as saying 4.29 times 10 raised -4. So we just have to move back 4 decimal places. Yes. Would we consider that to be very unusual?
Yes.
Yes. Yes.
So I guess anything that has 2 zeros would be considered, so like 0.00.
Yes. It's less than 2.5%. It's unusual.
Yeah.
So we have the ACT composite scores. They are normally distributed with a mean of 20.8, standard deviation of 5.6. We want to find the probability that the composite score is less than 19. So 19 is somewhere right here. Do we expect the answer to be over 50 or under 50%? Under. Has to be under. Could it be 1%?
No.
No, could be somewhere over here. So if you did normal CDF, what is the lower end point? The safest lower end point? Negative E99. The upper end point is 19. the mean 20.8,
You can't multiply it by that.
standard deviation is 5.6. What is that answer?
0.3738.
You're gonna get a probability.
0.3738.
Or no.
39,
39, yeah, yeah.
rounded to the fourth decimal place. Next, we have to find the probability of x greater than 21. 20.8 is right here. 21 is very close to 20.8.
Over 50.
So over 50.
Yeah, that's quite a little. Oh, wait, no, never mind, sorry, under 50. That's what I
So it's under 50% by a tiny bit, right? So how do we find that probability? We start at 21. The safest upper limit is,
Infinity.
the mean is 20.8, the standard deviation is 5.6. What do we get?
0.458.
Right? So as I went around, many of you got that part but had difficulties with this part. But this is actually very easy. So we know the probability that a person would have a composite score greater than 21 is 48.58%. I want to know if I picked 1,500, out of those 1,500, how many would have a score bigger than 21? So percent times the number of people. So we have 0.4858 multiplied by 1,500. What do we get?
729.
It's 28.7, rounded to the nearest integer, you get 729.
But you can't have 0.7 of a person.
Exactly. So